Okay, we're going to define or come up with a reasonable definition of the derivative, and we're going to show the process of differentiation by first principles. And it's an important video. So here we go. We've got f of x equals x squared again, because at this stage that should be a fairly easy one for us to analyze. Now the following process is true for any polynomial. Alright, so polynomials, you know what they are, hopefully, otherwise perhaps you shouldn't be watching the video. Basically they're strings of terms with x or something like that as the base in different integer powers. Okay, so x squared is pretty easy for us to analyze. I've got a rough sketch of x squared, and if you've watched the previous videos, some of these steps should be quite familiar. We've got a couple of points there. We're going to call one of them P, another one Q. Okay. Now we're going to generalize a little bit here because that's important in maths. And in general, this point, if we call this point a comma a squared, alright, I haven't fixed myself to a specific value, we can hopefully suggest that this is true for all real numbers. Okay, so alright, so hopefully we can suggest that it's not a proof as such, but it'll hopefully put up a pretty good argument that this is true for all reals. Now, we have in the past called the gap here H, and I'm going to stick with that. And thus the point Q, which is further along the curve, would be a plus h and a plus h all squared. Again, that's very similar to what we've done the last 2 or 3 videos, applying our ideas for a rate of change. And alright, you should know that the gradient, or the rate of change, the gradient PQ for this straight line from P to Q, which is a chord, is a plus h all squared minus a squared over a plus h minus a, and expanding, simplifying, cancelling and all that. So if you've watched this in sequence, this should all be pretty familiar. Okay, they cancel out. We've got 2ah plus h squared divided by h. We now cancel through. Okay, we get 2a plus h. It's a bit of a funny h. And the gradient of the tangent at the point P is the limit as h approaches 0 of the expression above, 2a plus h, and that would give 2a. Now a is just some general real number, so it would be true, this implies that it would be true for any value of x, any real value of x, certainly. Okay, and so therefore the gradient of the tangent for the curve f of x equals x squared is 2x at any point, because you can change a in the above example to whatever you like. And so there's actually a relationship there between this function and this function, which we'll see this video and into the next. Okay, so importantly, we say the derivative of the curve f of x equals x squared with respect to x is 2x. So that is where this term derivative comes in. So the gradient of the tangent is the derivative. So the derivative, in a sense, is a gradient function. Okay, so, and it applies for all points, certainly on this one, x squared, and that is true for all points on all polynomials. A relationship like this, not the same relationship, but a relationship like this will exist because polynomials are continuous. There are other sorts of functions, like for example reciprocal functions, where there's a discontinuity, and it's not always true for those, but for polynomials they're continuous, and there's a derivative at any point. Alright, so that at any point is true for polynomials and some other sorts of functions that are continuous. You will find in your further studies there are some functions that have points that have discontinuities, and you can't say it at any point. There'll be restrictions there. So in this example here, we're going to find the gradient of the secant and then find the derivative. Okay, so we're looking at that function there, x squared plus x. We're going to find the gradient of the secant and then find the derivative. Okay, after finding the gradient of the secant. So that should be familiar. Okay, gradient of the secant. Alright, so gradient of the secant, gradient of PQ. Same process, but I guess we better locate the points first of all. That would be handy. So for P we've got x and x squared plus x. Using the same h we've been using, we have x plus h and we have x plus h all squared plus x plus h. Okay, so here we go again. Whoops, that wasn't the best color to use. Forgive me for that. And we've got x plus h all squared plus x plus h minus x squared plus h. Put that in brackets because it's minusing both terms. Okay, and on the denominator we have x squared, x I should say, x plus h minus x. We have x squared plus 2xh plus h squared plus x plus h minus x squared minus x. And we have just h on the bottom. Is that getting familiar to you now? It should be. And what can we cancel here? We've got x squared gone. Alright, and we've got an x and minus x gone. Okay, now we can divide through by a factor of h. Now just be careful when you cancel out h like that, it does leave a 1 there. Alright, and that 1 is needed because it's part of a sum. Alright, and we have 2x plus 1 plus h is all that's left up there. Now apply the limit. As h approaches 0 is 2x plus 1. So therefore the derivative of x squared plus x with respect to x is 2x plus 1. So it's another function. Okay, one way of describing this derivative too, it's like a gradient function. We'll look at more at that in the future, but it's a function that describes the gradient at any point on x squared plus x. Okay, so the derivative can also be called the gradient function because the derivative itself is a function unless you're picking on one particular point. We're not in this, we're looking at it overall for the whole curve. So now this is important, we're going to define the derivative. So we have some general curve here we're going to call y equals f of x, and the gradient of the secant for this one would be f of x plus h minus f of x. This is the same process, right? X plus h minus x, where we can simplify the denominator there. So f of x plus h minus f of x over h. Now, if we apply the limit, it looks like this. And that is basically the derivative. Now it has a symbol, it has lots of symbols, but the one we're going to use with this function notation is this symbol here, f dash of x. That means the derivative okay, so that's a key point there. So the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h, and that is the derivative. It's the derivative of the general function f of x. Okay, so that's an important one. And I said just before we could call it the gradient function. So it's basically, it gives you the gradient of the tangent at any point. Okay, so for any value of x, provided the function is continuous, and for polynomials, which we'll deal with first, they are continuous. Now the process of finding the derivative is called differentiation. Okay, so we're going to use a process called first principles now, which is the long way, but you need to understand it because it's basically you can't understand what a derivative is unless you know this first principles. We will learn a rule soon, probably in the next video, that streamlines this, but first principles assists our understanding, so it's very important. Now the differentiation by first principles is basically applying that process, that result that we just highlighted a moment ago. That is what differentiation by first principles is. It's using that. So let's do two examples to finish off the video. So let's look at this example. So if we're given the function x squared plus 2x differentiate, which is the process of differentiation, differentiate by first principles. So that's what we're going to do. In other words, that's finding the derivative using first principles. Oops, derivative. Come on, stylus. Okay, applying the formula f dash of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Alright, so without drawing a diagram, can we come up with our points? So it's the limit as h approaches 0. Alright, so the points will be x plus h. You may need to do this separately if you're struggling with this, but this is the same as everything we've been doing previously. And I'm just subbing in the points as per previous. So if you've been watching all the videos, this should be dead familiar. Remember brackets around that because both of those terms will be subtracted. Okay, over h. You should have picked up by now, if you've been paying attention, that you always just get h on the bottom. So we might as well just stick with that. So in this case, we expand and we have x squared plus 2xh plus h squared. Distributive rule in the middle, and it's minus x squared minus 2x all over h, big long vinculum, there we go, and h, and let's see what we've got here. Don't apply the limit till you've fully simplified. So here we go, subtract x squared with x squared, we have 2x and 2x. Alright, now we can apply h and divide through by h. That comes down to 2x plus 2 plus h. Now we apply the limit. 2x plus 2. So the derivative is 2x plus 2. Last example, so given 2 minus x cubed, find the derivative using first principles. So let's go. Okay, so we get up to here, we need to find the points. So the first one will be 2 minus x plus h all cubed, and minus, now suggest you put that in brackets like I've been saying. Okay, and then we've just got h there. Okay, so be careful here. Again, if you don't know how to expand a cubic binomial, you might need to go squared, then times it by like this. In other words, square it, expand that out, and then times it by another x plus h. Otherwise, you might know that. And by the way, put all of this in brackets because it's all going to be subtracted from the 2. So we have x cubed plus 2x squared h, sorry, 3x squared h, 3x h squared plus h cubed, minus 2 minus x cubed all over h. You're probably getting sick of writing the limit as h approaches 0. Okay, just speeding that up there. And now we divide through by h because we've simplified the numerator. So it's the limit as h approaches 0 and that'll be of negative 3x squared minus 3xh minus h squared. Now we apply the limit. So I just put a little orange line there because a couple of my lines ran a bit close together, and the only term, these terms here have a h, so that they approach 0, so that means it's just negative 3x squared is the derivative. So f dash of x, the derivative, is negative 3x squared.